Okay, good morning. I'm doing this video here to give you the second page of the 7B notes. The first page of the 7B notes, you'll just copy the vocab that I put up on the board. Second page, I wanted to do a video because I kind of wanted to break all this stuff down. So I'm going to put the definitions in here in these blanks, and then we'll go to GeoGebra and sort of um, uh, you know, prove these things sort of one by one here, okay? So, first rule is if a radius is perpendicular to a chord, okay, it bisects it, okay? So if a radius is perpendicular to a chord, the radius will bisect the chord, all right? So if we were to look at a circle right here, all right, let's say we have this chord AB, all right? Now, if we have a radius that's perpendicular to it, okay, if we have a radius that's perpendicular to it, okay, what it'll do, it'll cut AB into two congruent pieces right there, okay? And we'll prove that a little bit more when we get to GeoGebra here. I wanted to sort of put these definitions here right now. All right. Our next rule, okay? If two arcs are congruent, their chords and central angles are also going to be congruent to each other. I'll come by in a little bit.
That's actually what I'm trying to do.
I'll be right there. Okay, I'll be there in a minute. I'll show you. All right. So if two arcs are congruent, their chords and central angles are also congruent to each other. Okay. Next, the measure of an arc is equal to the measure of its central angle. Okay. And then just to talk about that real quick. So if we have, an arc here, let's say this is an 80-degree arc of a circle. Okay. Well, if the angle is in the center of the circle, that angle is also going to be 80 degrees, which is pretty self-explanatory because all the angles around here around the center add up to 360 and the full circle adds up to 360, okay? Last rule, if a segment is tangent to a circle, okay, then it is perpendicular to the radius at the point of tangency, okay? So I'm going to go over here to GeoGebra and sort of show you guys one by one how to do this and really how to prove this stuff, if that makes sense. And then we can, I'll give you guys a little bit of time to sort of mess around with it. And we're not really going to get into much of this stuff today or all of the vocab today. I just wanted to give you guys all the vocab sort of here at the beginning. Of this thing here. So let's move on over to all right. So let's do a circle with a center right here. So we'll just do a center, pull that circle out right there. Okay. So all you got to do is hit circle with center. You'll click and then you'll drag it out. Okay. So we have a circle with our center right there. Okay. So radius perpendicular to chord, then it bisects it. So let's do a chord. So let's just make a segment right here. We'll put it on circle. So we'll see, drag it down there to where it's right on the circle there, point D. Okay. All right. So now we're going to do a radius that's perpendicular to CD. So let's do a perpendicular line. To CD. Hang on a second. Perpendicular line. So select point. So we're going to go through point A. Hang on, I apologize for that. Perpendicular line. We're going to hit it from point A. And we're going to hit it, go through point CD. Okay. So now we have a radius that's AE. Okay. And it is perpendicular to CD. All right. Now, if we do another point right here, point F, okay, we can measure the distance from C to F, D to F, and we see that it is the same. Okay. And if we're gonna move any of these points right here, okay, if I were to move this chord CD, okay, that radius will sort of move with it, and you see that CF and DF are always going to be congruent to each other. So the radius being perpendicular to a chord is going to cut that chord in half, no matter where that chord is. Okay. If you want to rewind that and see that one more time, and I could do that again one more time for you guys here. So we have our circle, all right, and let's just say we decide to do a chord, so we'll hit a segment from C and point D on the circle right there. All right, next we do a perpendicular line. We're going to click point A, which is the center, CD, which is a perpendicular line, make another point. All right, find the distance from C to E and distance from D to E. All right, and as we move the chord around and the radius sort of moves with it, we see that the radius is cutting the chord in half, and it's automatically perpendicular because we use that kind of thing here, okay? And what we're going to do later on is now, all radii are congruent. If we do a radius from A to C and a radius from A to D, well, now we have, a couple of right triangles here that are congruent to each other because I have a hypotenuse that's congruent and legs that are congruent to each other. Okay, so you can mess around with that a little bit if you'd like to. And I want to go to our next rule, okay? So if two arcs are congruent, their chords and central angles are also congruent. I'm going to skip that one for right now. This is kind of hard to do on GeoGebra. The measure of arc is equal to the measure of the central angle. That's kind of self-explanatory. So let's look at the last one. If a segment is tangent to a circle, then it is perpendicular to the radius at the point of tangency. Okay, so I'm going to move down here and just create a new circle. So click new circle with a center at point G right here. Pull it out. Okay, and there should be a tangent line here. If we go down to more, I know there's a tangent thing in here. Here we go. So construct tangents. So I'm going to click a point, make a point outside here. All right, so we're going to click this point and click that tangent line right there, okay? So this point I, we're going to do a tangent line from I to the circle right there. It happens to go through point H. If we were to move that thing, then there's that, okay? So there's a tangent. See, tangent line just touches the circle only once, okay? Now if I move a point, make a point there and a point there, right? Now, the rule is the radius is perpendicular, okay? It's perpendicular to the tangent at the point of tangency. So let's say we do a segment right here, a radius that goes from G to K, all right? And then we want to measure the angle. So if we measure the angle, we can go to measure angle I, K, G, all right? We see we have a 90-degree angle here, okay? And no matter what happens as we move this, okay, and we see the radius kind of moves along with it, okay, the radius and the tangent are perpendicular to each other at the point of tangency. Remember, the point of tangency is this point K or this point J right there, where the tangent line touches the circle, okay? So where the tangent line touches the circle, okay, it will be perpendicular to the radius when we have a radius that touches that point as well. That's something that we'll do more with triangle proof sort of as we go. That's just a cool little thing there where we can kind of see that. Okay. All right. So that kind of takes care of that. And so I'm going to clear this board right here. And if we're looking at our definition, okay, if two arcs are congruent with their chords and central angles are also congruent. So let's say we want to construct a circular arc. I don't know if we can prove this over here on GeoGebra, but let's just try to do another circle here. I have an idea. So we'll do a circle. All right, from A to B. So let's just make a couple angles here. All right, and so we'll do a radius from A over here to point C. Whoops. All right, and if we wanted to make an angle, let's say we wanted to make a 40-degree angle or something like that. All right, so this 40-degree angle will take us down to point C. So we'll do a segment here from A to C prime right there. Okay, so now we have this arc from C to C prime. Okay, now let's just say we have another arc. All right, we're gonna do another 40-degree arc. So we'll do a point here, and we'll do another segment here from A to D. Okay, and we'll do another angle with a given size. We'll do a 40-degree angle there. And so now that'll take us to D prime, okay? So now we have two arcs. We have C to C prime and D to D prime, okay? Now, so we have two congruent arcs, okay? Because they're from the same circle, we have two congruent angles. They have a 40-degree angle, 40-degree angle. So this arc is going to be congruent to this arc. But also, if we were to do a chord, so let's say we do a chord from C to C prime. All right, and then we do another chord from D to D prime. All right, and we were to measure these things. All right, from C to C prime is going to have a length of 3. From D to D prime also has a length of 3. Okay, so if we have congruent arcs, which C to C prime and D to D prime are congruent arcs, okay, they have congruent central angles, 40 degrees, okay, and they have congruent chords, okay. So the arc would be this rounded area from C to C prime, okay, and from D to D prime, okay. The chord would just be the straight line that cuts straight through from C to C prime and D to D prime. Okay, I don't think there's a way on here to measure an arc, so I don't think we really do that. We could talk a little bit more about arc lengths later on in the second part of these notes here. So we took care of bisects, we took care of this, measure of an arc equal to the measure of central angle, and we did the perpendicular thing right there. So if you want to use GeoGebra and sort of fiddle around with it on your own and come up with some of that stuff on your own, that's cool. And then we'll go from here, and I'll give you guys this arc length thing over here as well. Okay, this is a pretty simple deal. Okay, so an arc is just a fraction of the circle's circumference. Okay, if we're trying to find the length, it's a fraction of the circumference. The degrees of the arc divided by 360 gives us the fraction. Okay, so whatever degrees of the arc